Hi everyone. So this is the very last process that we have to go through for respiration. So this section, which is section 7 of chapter 23, is going through gas transport. So remember we started with pulmonary ventilation, and then the next thing that we moved on to was alveolar gas exchange. And in that same section we talked about systemic gas exchange, but remember gas transport is in between the two the two gas exchanges, because remember that once we get oxygen from the alveoli into the bloodstream, we got to move it around to get it to the systemic cells. And once we pick up carbon dioxide from the systemic cells, we got to move it around in the bloodstream to get it to the alveoli. And this is what this section is concentrating on, is going to be gas transport. Some of this is going to be obvious, right? Like oxygen. We know how oxygen is transported around. But what's surprising is actually not all of it. 98% of oxygen is going to be transported in within the erythrocytes. Remember, you have the hemoglobin, and hemoglobin is going to have those 4 iron molecules, and that is where oxygen is actually going to attach. It's going to be on those molecules. But also the fact that you have this solubility coefficient. Remember that anytime that a gas comes into contact with a liquid, it is going to, depending on like the solubility coefficient, is going to be soluble in that liquid. So remember, oxygen solubility coefficient was very low. So that means that there's not a whole lot that's going to be dissolved in plasma, but there's still going to be some, roughly 2%. The book says a little less than 2%, but roughly 2%, and this is 98%. So remember that oxygen bound to hemoglobin is called oxyhemoglobin, and it's denoted by, So yeah, I think that's right. It's going to be shown by using this, HbO2. And anytime that you have a hemoglobin without oxygen bound to it, it's called deoxyhemoglobin. So you can have this kind of equation that's happening where you have your deoxyhemoglobin, and it's going to attach oxygen at the alveoli, right? And then that is going to become HbO2, which is oxyhemoglobin. And see how it's reversible? That's why I put these weird little arrows right here, is once it gets to the systemic cells, it's going to dump off the oxygen and turn back to deoxyhemoglobin. So now let's talk about the other important gas, which is going to be carbon dioxide. Carbon dioxide has 3 means of transport. So remember that carbon dioxide has the highest of our gases. It's going to have the highest solubility coefficient. So that's why we have more that's going to be dissolved in water, more than oxygen. So 7% is going to be dissolved in, I said water, but it's really because most of plasma is going to be water. You have some that can detach to the globin portion of the hemoglobin. So when that happens, when CO2 attaches to hemoglobin, remember that it is going to be something called carbaminohemoglobin, so HbCO2, 23%. The rest of it, 70%, is going to be found and disguised as bicarb. You guys remember what bicarb is? HCO3. You see it? It's disguised. So you can kind of see CO2, so there's just an extra hydrogen and oxygen attached to it. Let's take a look at this process. So this is what happens from the systemic cells. Once the CO2 diffuses to that erythrocyte, inside it binds to water. And when that happens, with the help of something called carbonic anhydrase, it is going to form carbonic acid. This is what H2CO3 is carbonic acid. So immediately carbonic acid is going to split into bicarb. Here's a bicarb. There it is. It's disguised as a bicarb. But look, what another thing. It's going to be hydrogen. So you might remember this from an earlier section where we talked about how this is not good for our CSF or our blood because of what's happening here. Another interesting thing is that the hydrogen can actually hook onto part of the hemoglobin as well. So it can hook onto the globin part of hemoglobin. What else on here? Oh, so when bicarb leaves that erythrocyte, it's always exchanged with a chloride ion. So this is called the chloride shift. So that's kind of interesting as well, that anytime that bicarb moves out, chloride is going to move in. Let's see. Oh, so let's take a look and see how this is going to, because we can't exhale this out. So it's going to travel around, 70% is going to travel around like this in the bloodstream, but we can't exhale bicarb out. So let's take a look and see what happens once it gets up too close to the alveoli. It is going to be converted back. So again, we have this little chloride shift that happens again, where you are going to have that bicarb moving into the erythrocyte and chloride moves out. And it does the same thing. It combines, the hydrogen is released from the globin part of hemoglobin. It combines with hydrogen ions to form carbonic acid. With the help of carbonic anhydrase, this enzyme is going to convert it back to CO2 and water, and then that diffuses out of the erythrocyte and it leaves into the alveolus. So it's interesting how this kind of whole process is going to take place and how it can move around disguised as CO2 like that. So let's take a look at hemoglobin as a transport molecule. We talked about oxygen. That's attached to the iron. I just mentioned that carbon dioxide can attach to the globin, and now I just mentioned how hydrogen ions can attach to the globin portion as well. So that's kind of interesting. So anytime that one or more of these substances binds or releases, either one, whether it binds to the globin or what we saw with hydrogen ions here, see it's binding here and it's releasing there. Anytime that one substance or more binds or releases, it actually causes this change of shape in the hemoglobin molecule. And the reason why that's good is it can influence the ability of the hemoglobin to bind or release the other two substances. So that means that if we'll talk about how sometimes when, let's say, hydrogen ions binds to part of the hemoglobin molecule, that kind of changes the shape and allow it to bind carbon dioxide or something like that. So that's kind of the idea that's going on there. Let's take a look at, see what happens specifically for oxygen, since really hemoglobin, one of the main things is oxygen transport. That's what we're going to concentrate on a little bit more. So each hemoglobin, if you remember, if we went back to this and counted how many oxygen molecules it can hold, look, 1, 2, 3, 4. It can hold a total of 4 oxygen molecules. So, which, I mean, think about it. You are going to have, where are we? We're right here. Think about it. You're going to have millions of these hemoglobin molecules inside of one red blood cell, and then you have trillions of red blood cells. That's a lot of oxygen, right? Yes. So this percent oxygen saturation of hemoglobin, what this is basically telling us is the amount of oxygen that's bound to this available hemoglobin. So this is what I mean. If oxygen is bound to 1/4 of the available iron binding sites, that means it is 25% saturated. If all 4 of the iron binding sites are full of oxygen, that means it is 100% saturated. So that's what that whole percent saturation is going to refer to. What's interesting is that hemoglobin is going to have this cooperative binding effect. And that means that when one oxygen attaches, other oxygens want to bind as well. So that's really going to help us to carry a lot more oxygen and get it to that 98% saturation level. So this whole thing can be charted, can be put on a chart called an oxygen hemoglobin saturation curve. Another term for that is oxyhemoglobin dissociation curve. And I'll put that up. I don't want to write that out, but I'll put it up here. Or it should be appearing already. So let's take a look at what this curve is going to look like. It's S-shaped, nonlinear, as you can see. So look, remember that hemoglobin is saturated at 98%. So there's 98%. That's exactly what we have, 98%, and the PO2 at 105, which is about what we have in the alveolus, right? If I went back to the slides to look at how much the PCO2 is in the alveolus, It's right around 105, 104 to 105. And so if we have a PCO2 at 104, 105, we are going to be fully saturated 98%. I know you're thinking, that's not fully saturated. 100% is fully saturated. Remember, let's go back to this. So where is it? I just passed it up. 98%. Only 98% of that oxygen is going to be transported. The other 2% is dissolved in plasma. So let's take a look at what happens down here. So you have this huge, steep, large change at first. So from 0 all the way up to what, right about 60, you're going to have this really large change in saturation that's going to occur. See? It's a big old change that's going to occur. It has a lot to do with this right here, this cooperative binding effect. You're going to start to have some oxygens hop on, and then they're all going to want to hop on after that. So we're going to talk about actually your saturation really doesn't dip that low. I think the most, well, just during restful periods, we're going to talk about how really the most it gets down to is 75%. But hey, we got to talk about this oxygen saturation curve. So anything higher than 60 millimeters of mercury, here's 60 millimeters of mercury, you're just going to have a little bit of a relatively small change after that. But again, hemoglobin saturation, 98%, is fully saturated. You don't get to 100% unless you're in some kind of hyperbaric oxygen chamber, and they can go in and get you at 100%, but they have to put you in one of those special chambers. That's how decompression sickness is going to be treated, is through one of those. Let's take a look and see what this has to do with altitude. So this is the issue with altitude. So with altitude, you are going to have changes in your total atmospheric pressure, which means that you have less oxygen, which means that you are going to have a change in these numbers. If you have a change in these numbers, that's going to cause issues with the percent oxygen saturation of your hemoglobin. So let's take a look at how this is going to be, affect you. All right, so 5,000 feet. 5,000 feet is like Boulder, Colorado. They are at 5,000 feet. The atmospheric pressure in Boulder, Colorado is 632 millimeters of mercury. It's not 760. Because of that, we don't get that 104, 105 right here. No, we do not. Look, it's only 81 millimeters of mercury. That causes an issue for a couple of reasons. Remember that we talked about how you have the little alveoli with proper gas exchange to occur, the most efficient gas exchange to occur. You want to have a steep gradient, actually. You want it to be 104 in here, and you want it to be, it was down to 40 over here, if I remember correctly. You want a nice big saturation, a big, huge pressure gradient happening. When you decrease this, you still have some oxygen that's going to go in, but the gradient's not as big. So you're not going to have as many oxygen molecules that are going to want to go. But another issue and it's not a huge issue because look, it corresponds to a hemoglobin saturation of 95. Where did I get that? Okay, 81, 95. That's not too bad, right? 95% hemoglobin saturation is not shabby at all. So really, there's usually not issues here. Let's say that you're climbing up in altitude. You are going to, let's see, Aspen, Colorado is 8,000 feet. And then you go to Pikes Peak, that is at 14,000 feet. Remember, as you're going up in altitude, this number is getting less and less, and so is this number. It's getting less and less as well, and you're having issues with gas exchange that's going to occur. So 17,000 feet is between Pikes Peak, which is 14,000 feet, and Mount McKinley, Alaska, which is 20,000 feet. What happens here is that you have a huge drop, 40 millimeters of mercury. So if you go here, 40 millimeters of mercury, you have a 75% hemoglobin saturation. So that's when it becomes an issue. This is when usually right here, this is when you have those chemoreceptors, those peripheral chemoreceptors saying, hey, what happened to the oxygen level here? We were at, 90. Remember, once it gets to the systemic cells, it's about 96. And here it's 104. So let's just say, hey, we were at 104. What the heck happened? We're all the way down to 40. This is the big, substantial oxygen change that I was talking about way back in the nervous, whenever we were talking about the nervous control of breathing and how you have to have a huge change in oxygen. Here it is. This is the huge change in oxygen. So yeah, if you have these big changes in altitude, it will actually trigger your breathing, your respiratory rate to increase. So that's one of those instances where it is going to happen. But remember, the biggest stimulus is carbon dioxide. This is going to be the instance where oxygen actually triggers it. So you can imagine going to Mount Everest. I think they said it was it 29,000 feet? Yeah, I'm pretty sure it's 29,000 feet. So you can just imagine how low this number gets. That's why whenever you see people on Mount Everest, they have their little oxygen masks. Yeah, because you're not going to be able to breathe out there. There's not enough oxygen and to help you out. So that's why with altitude sickness, some mild symptoms of altitude sickness is headache, nausea. This is bad altitude sickness. This is when there's issues and you really should do something about it. This is even worse, cerebral edema. So it can eventually cause cerebral edema. But some people, if they just kind of go to Colorado, even going to Boulder, it's not a big issue. But if you keep going up and up, like if you go to Pikes Peak, that's when some people can have altitude sickness. Some people don't. We took a vacation to Colorado a couple of years ago, and my husband had some issues with headache and nausea. Me and the kids, we were fine. So it doesn't matter if you're male, female, young, old, your health, asterisk on that one, right? Anybody, altitude sickness doesn't really care who you are or what you are. It's just going to hit just random people. So just make sure that you stay hydrated, drink lots and lots of water. And if you need to, you might have to go down elevation. You might have to go back to Boulder or Denver, and so you can go back and get to that, what you need. So let's take a look and see how this oxygen saturation is going to occur. Or how it's going to be released. Look, 98% when it leaves the lungs. When it leaves the lungs, what it's doing is it's going in and it's dumping off oxygen, right? It's going in saying, hey, cells, here's some oxygen. Hey, cells, here's some oxygen. So by the time it's done dumping off oxygen, it's still 75% saturated. That's a whole lot. So as you can see, it's never truly deoxygenated. Only 20 to 25% of oxygen transport by hemoglobin is released. So that's really good because of the fact that this is going to be known as an oxygen reserve. So you're always going to have a little bit of oxygen, not a little bit, it's a lot, right? It's a lot of oxygen that remains bound to that hemoglobin after passing through the systemic circulation. So it's just, again, it's additional oxygen. Anytime that your body undergoes an increased demand, it is going to, you have some backup, like for vigorous exercising. You're going to have a huge drop in PCO2. So I think it drops to 20 millimeters of mercury. If I'm remembering correctly, but yeah, you're going to have a significant drop. So, but the reason why, but that's in the systemic cells, so not in the bloodstream itself. Sorry, my mind's wandering again. But what happens, the reason why, it's because you need more oxygen to be unloaded and go to the tissues. So the blood leaving the capillaries and very active muscles is only about 35% saturated compared to 75% at rest. So you can see, look how big of a drop that is. Let's take a look and see what causes oxygen to even leave. So see what we have here, it's at 98%. It goes to 75%. Where is it? 98% to 75%. Exactly what we saw in the last section. let's take a look and see how it goes from there to there. What causes the oxygen to want to leave the hemoglobin and go to the tissues? That's what we're going to look at. So one of them, of course, is oxygen levels, right? If the systemic oxygen levels decrease, so if the oxygen levels inside of the systemic cells decrease significantly, like with like with vigorous exercising, they are going to want to leave hemoglobin a lot faster and go to the systemic cells. So that's one thing, is this big drop in PCO2 in the, so let's draw it out to get a better picture, because I feel like I'm not explaining it very well. So here's our cells. Let's say that these are some very active muscle cells. And normally, remember, normally it's only it goes to about 40 millimeters of mercury. But this, let's say it goes to 20 millimeters of mercury. This is basically saying, hey, I need some oxygen, right? Here's the bloodstream. Remember, it's coming into the bloodstream about 95, 96. So look, it's able to, and again, this is not percent, this is millimeters of mercury. Remember, it drops. I know you're saying, Ms. Watson, you're crazy. Look, it's at 105. But remember, we talked about in the last section how by the time it gets to the systemic circulation, it's dropped to about 95, 96 millimeters of mercury, which is not bad because, look, you're still like 97.5% saturated, so it's not a big deal. But that's going to cause more oxygen to be released from the hemoglobin than normal. Because remember, pressure gradient is the key. If it was only 40, it would only dump out enough until equilibrium is reached. But this is a big difference. So it's just going to keep on dumping and keep on dumping until equilibrium has been reached. So that's one thing that causes oxygen to want to leave the hemoglobin, is oxygen levels of the tissue. Another thing is, let's take a look at this picture instead. There it is. There it is. PO2 levels within the blood and the systemic circulation. So this is showing systemic circulation right here. But again, if this drops to 20, it will drop out even more. So right now it will allow it to leave normally until 75% is reached. But again, if it's 20 and if this decreases to 20, lots more is going to be released. Temperature is going to cause it to be released. Usually it's kind of an indicator that exercise is occurring. This is exactly what you want happening. I mean, the body is amazing in the fact that, hey, more oxygen is being released because these muscles are active, so we need to have more oxygen. Okay, well, I'm going to dump off more oxygen. Hey, these tissues are heating up because they are undergoing lots of cell respiration because they are so active from exercising. We need more oxygen. Okay, we'll dump more oxygen over here. So that's another thing. Temperature increases more oxygen being released. I kind of think about it as more people getting off the bus. You know, when you're in the alveoli, oxygen is loading up on the bus, right? It's like a full train ride in the morning to come to El Centro. And then once you get over here down El Centro, you have kind of this mass exit, or just, you know, little spots along the way you're going to have people exiting. And that's what's happening here, is oxygen is going to exit the bus and go and to these tissues, so the tissues can use the oxygen for cellular respiration. Hydrogen ions, if they increase, again, really what's happening, vigorous exercise can cause an increase in hydrogen ions over here in the systemic cells because that produces lactic acid. So that's another thing that can cause it to, hey, we need more oxygen. There's lactic acid being formed over here because we don't have enough oxygen. Okay, here's some oxygen. Don't worry about your 2,3-BPG. Carbon dioxide will also cause it to release. So anytime carbon dioxide comes in and binds to the globin part of the hemoglobin, it's like oxygen is disgusted by it and it wants to just leave and go to the systemic cell. But where's this carbon dioxide coming from? It's coming from these tissues, right? Yes. So the more carbon dioxide you have, then they can bind to the CO2. Remember, they can bind to the hemoglobin. There's other places that carbon dioxide can go, but this is one thing that will cause the oxygen to leave. Because where do we talk about it? Oh, right here. The binding of one substance causes a change, and it influences the release of one or the other two. So that is going to be why this happens down here. Don't worry so much about the shifts. The book talks about, oh, it causes a shift to the left. Hey, it causes a shift to the right. Don't worry about that. So this is it. This is what we covered, and it seems like so long ago, right? We went through pulmonary ventilation, and then we talked about how we inhaled, and once we inhaled, how alveolar gas exchange was going to occur. The oxygen is going to leave the alveoli and go into the bloodstream because of that partial pressure gradient. And then it's going to be transported either in the plasma or on a hemoglobin. And then it's going to be released. Why is it released, Miss Watson? Because of these things. That's why it's released. What does it do at the same time? It picks up carbon dioxide. So again, carbon dioxide, it's going to, just like this one, it's because of the partial pressure gradient. But so because of the partial pressure gradient, carbon dioxide is going to diffuse into the bloodstream, and then it's going to travel around in those three different ways. See, attached to hemoglobin, dissolved in plasma, or disguised as bicarb. And then it's going to go all the way to CO2, and it's going to go down the partial pressure gradient so we can exhale it out. Whew. That was a lot, right? So these are nice little causes of respiratory homeostatic imbalances you might want to kind of look over and see if we hit a lot of them. Asthma, there's pneumonia on there, emphysema. It shows some of the issues that is going to occur because of it. So one more section, we're going to take a look at breathing rate. We're going to talk about how hyperventilation, hypoventilation is going to change the blood composition, chemical composition. And then we're going to take a look at what else is in there? A little bit of exercising. So until next time.